Hello everybody, I hope you are doing well today. Today's video lesson discusses lesson 10-2, simplifying radical expressions. Your assignment was on page 631, numbers 1 through 15 odd. Now some of you have seen these radical expressions and simplifying them on the ALEKS topic, so you might have a good idea on how to do them. If not, you're in the right place. So with numbers 1 through 9, odd, you are having to simplify the expression, right? And in order to simplify it, you have to kind of take out a perfect square out of the radical, and you have to simplify it down till it can't be simplified anymore, right? I'm going to show you two different methods. One's a basic method that will work every time. The second method might be a little bit trickier, but it makes it quicker if you know what you're doing. So, number one, we have the square root of 24, and I need to simplify this expression. So to simplify it, I need to take out all the perfect squares possible in the square root of 24. So in the square root of 24, the basic way to do it is to just break it down into all the factors of 24, right? All of the factors, all the prime factors, right? So the basic one we can do is 2, right? We know that 2 times 2 is 4. Right? Then 2 times, and then times 2 again, that's 8. And then how do we get to 24 from there? Well, we times it by 3, right? That is all the prime factors of 24. And then from here, what you have to do is you have to figure out, okay, 2's, right? There are 2 2's here. So if you have 2 of the same number, you can pull it outside the radical, right? We're taking the square root of those, so we're going to pull out a 2. So this is really going to be 2. And now since 2 and 3 are left, we can't take anything out of those, so we just multiply them together, and we get 2 root 6. Now that would be the simplified form for number 1. Now, another way you might want to think about it, instead of breaking it down into all the factors, maybe you just want to break it down into perfect square factors, right? For example, the square root of 24 I know is 6 times 4, right? And out of those two, we know that 4 is a perfect square. Well, what's the square root of 4? Well, that's 2. We can take that out. What's left? 6. There's no perfect squares there, so we leave it inside the radical. So those are just the two different ways you can go about these problems. I prefer the second way because it's a lot quicker when you really start getting into those higher numbers with lots of factors. But it's completely up to you on which method you want to use, right? I'm going to do another example. For example, let's do number 5. We have the square root of 3 times the square root of 18. So like I said, there are two different ways that you can do this one. One, you can actually go through and you can multiply 3 times 18, right? You could actually do that and then break it down into factors. However, maybe you just want to leave them separate for now, right? And then break it down into, okay, I know that square root of 3 is going to stay there, but 18 can be thought of as the square root of 3 times the square root of 6, right? Because 18 is 6 times 3, right? Since I have the square root of 3 twice, we can pull out a 3, and then what are we left with? The square root of 6, right? So number 5 would be 3 times the square root of 6. When you start getting into variables, remember a perfect square variable is any time that you have the same variable, right? If we're multiplying it, right, a times a is a squared. So a squared is a perfect variable. Maybe you have a to the third times a to the third, so that would be a to the sixth, right? So you're looking for all of those types of variables. So for example, like number 7, we have the square root of 60 x to the 4th y to the 7th, and we need to simplify this as much as possible. So if you want to think of this as 3 separate things, you can. So square root of 60 times the square root of x to the 4th times the square root of y to the 7th, right? You could think of it as 3 separate things. Alright, so let's start with the variables because I think those are the easiest. The square root of x to the 4th, well, we have to find 2 things that multiply together, 2 variables that multiply, but when we multiply the variables, remember we add the exponents. So, for example, here, x to the fourth, well, that would be x squared and x squared, right? So what number I would pull out here would be x squared. That would be outside of the radical sign. So this part's done. Now y to the seventh, we need to figure out, okay, well, y to the third times y to the third is y to the sixth, and then we're left with an additional y. So we're going to pull out a y cubed, and then inside the radical sign, we're going to be left with an additional y. And now we have one last one, which is 60, and I'm going to use the method that I prefer the best. And I need to figure out, okay, what perfect square will go into 60? Right, and you could go through the possibilities. I know that 6 times 10 is 60, but neither of those are perfect squares. 12 times 5 is 60, but neither of those are perfect squares, so that doesn't help me. So I just need to keep going through my lists here. And maybe I need to use 4. 4 times 15, right, is 60. So if I use 4 and 15, right, we know that 4 is a perfect square, so we can pull out a 2. And in 15, there is no perfect squares left because we're just left with 3 and 5, and those are prime. So we're left with 15 inside of the radical sign, and we took that 2 out. So we're left with 2x squared y cubed to the square root of 15y. Okay? So that should kind of help you out with number 9. And then the last set here, we are simplifying expressions with radicals in the denominator. Now, I know having radicals in the denominator doesn't seem like a big deal, but it's very confusing when we start dealing with operations, right? Next lesson we'll talk about adding and subtracting. And if you think about adding or subtracting with a fraction, we need common denominators. And that's very difficult if we have a radical in the denominator. So just lots of reasons why we don't like radicals, but for the main reason, it's just difficult to deal with. So we're going to get rid of it. So to simplify these, we have to use what we call the conjugate. The conjugate is a multiplicative term that we can use to make a denominator rational. Right? It's a term we multiply by to make it rational. So for example, like number 11, we need to simplify this. So we have 3 over 3 plus the square root of 5. Now, in order to rationalize this, we have to multiply both the numerator and denominator by the conjugate. Now, the conjugate is the same expression, but if it's a plus, it changes to a minus. So, for example, where we have 3 plus the square root of 5, we're going to multiply it by 3 minus the square root of 5, both on the top and the bottom, or the numerator and the denominator, right? And the reason that this works is a couple different reasons. One, notice we are really multiplying by 1 here, right? 3 minus the square root of 5 divided by 3 minus the square root of 5 simplifies to 1. So that's the reason why it works. Whatever you do to the top, you can do as long as you do the same thing to the bottom. But it also works here because, think about difference of squares, it'll make it rational by eliminating these terms. So, if I multiply it across, I have to multiply the numerator. So 3 times 3 minus the square root of 5 is going to be, well, 9 minus 3 root 5, right? Now, I know that seems odd. We were trying to get rid of a radical sign, but in order to get rid of it in the denominator, it has to move to the numerator. So that's going to be my numerator now. And my denominator is 3 plus root 5, and then 3 minus root 5, right? And if we think about foiling, right, factoring out, 3 plus root 5, I would have to go 3 to the 3, and then 3 to the minus root 5, and then vice versa with the square root of 5. But since they are difference of squares, I can take the easy route. 3 times 3 is 9. And then square root of 5 minus times negative square root of 5. So that's just going to be the negative square root of 25. But we know that the negative square root of 25 is just 5. So we're going to be left with 9 minus 3 root 5 over 9 minus 5. And 9 minus 5 is 4. And then that would be my fully simplified expression for number 11. I'm going to do one more, just an example with kind of little explanation. That way you can just see what it looks like. And I don't want to have to confuse you any more than maybe you already are. So for number 13, we have to get rid of the 1 minus the square root of 10. So we multiply by the conjugate. The conjugate would be 1 plus the square root of 10. So we do that on both the top and the bottom. And in which case I would get 2 plus 2 root 10 in the numerator. And then the denominator would be 1 minus the square root of 100. But in this case, that would just be 2 plus 2 root 10 over 1 minus 10. And we know that 1 minus 10 is negative 9. And then 2 plus 2 root 10 stays on top. Okay? So that's kind of the idea behind it. And if that's confusing, please let me know. Send me an email. And I also have the office hours open later this week on Zoom. And yeah, so I hope you have a great day, and thanks for watching.